So this is MHSET 2025 nuclear physics questions. So first we read the question. The question says that the ratio, this is the pairing term ratio, which is used in semi-empirical mass formula for binding energy. So what will be the value of this ratio? It is asked. So we know that for binding energy, we have a very large formula, which is basically volume energy term, surface energy term, Coulombic energy term, asymmetric energy term, and pairing energy term. So in this question, this term, pairing energy term ratio is asked. So one by one, we will see the relation of this energy term with respect to the atomic mass. So EV directly proportional to A, surface energy term directly proportional to A2 by 3. Similarly, Coulombic A to the minus 1 by 3, and asymmetric A minus 2z z whole square divided by A, and pairing energy term is proportional to 1 upon A 3 by 4. Now, this pairing energy term has three cases. Means, if in case first, if our number of neutrons is even and number of protons is even, say 4 4, then this will be EP equals to plus AP upon A, means this positive sign will come. If N and P both are odd, then it will come EP equals to minus AP divided by A3 by 4. Minus sign will come for the energy term. If N is even or odd, or P is odd or even, so EP equals to 0. So in our question, it is given nitrogen 15 7. So 7 is the proton. So 7 is the proton, then 8 is the number of neutron. So 1 is even, 1 is odd. So EP equals to 0. So numerator is 0. So we don't care about the denominator. So the energy term for pairing is 0. So answer is 0. Let's come to second question. So we read this question. A radioactive source with half-life of 69.3 seconds has an activity of 1 microcurie. How many radioactive nuclei will remain after T equals to 69.3 seconds? So we are given a radioactive source which have half-life of this. So basically it's a formula-based question. But first we have to convert this microcurie into becquerel. So SI unit of radioactivity is becquerel. So 1 curie equals to 3.7 into 10 to the power 10 becquerel. Okay, so what is becquerel? The becquerel represents the number of unstable atoms in a radioactive sample that decay over a given period. R equals to lambda n. So first we will convert the activity in the SI unit. So microcurie is converted into becquerel. Now lambda equals to 0.693 by, means this is what ln2. ln2 by half-life equals to lambda. So we calculate, it comes 10 to the minus 2. Then again activity formula we take this activity. So R equals to lambda n naught. So we calculate n naught, means original number of atoms at T equals to 0. This is 3.7 into 10 to the power 6. So what in question is asked? How many radioactive nuclei will remain? So this basic formula n equals to n naught E minus lambda T, you will get the n. So this is the number of atoms will be remain after time 69.3 seconds. Okay, let's come to third question. An alpha particle with energy of 6.17 mega electron volt is emitted from a neutral radioactive source, which is californium, through a process of quantum tunneling. So this process is classical forbidden. Estimate the classical barrier range through which the alpha particle escape through a tunnel process. So, hmm, basically, this is the reaction. This is the reaction. Okay, let me give this. This is the reaction. Californium atom is decayed into curium and plus alpha, and which have energy 6.17 mega electron volt. So what in question is asked? So there is a so basically this is CF atom, CF 251. So it releases a alpha particle. Alpha particle is releases alpha particle. So it is given that this happened through a process of quantum tunneling. Quantum tunneling. And this is classical forbidden process. Why is it so? So quantum tunneling, we will see that why this alpha particle escapes through quantum tunneling, not of classical forbidden. So actually, what happens that the when alpha particle release, so there is a electrostatic force, the potential. So the potential is say V is greater than 6.17 MeV. So the energy by which the alpha particle releases is less than the potential. So still the potential is very much. How this alpha particle escapes? So it is because of quantum tunneling. Quantum tunneling. It says there is a slight possibilities. All quantum phenomena based on probability. So there is slight probability or possibility to escape. So let's see. So first, so this is first we will calculate the radius. So radius is calculated r equals to r naught a 1 by 3. So this is the radius. Okay. Now this is the radius of this atom. So we will calculate the potential range. What is the Coulomb potential? So VR equals to this formula 1 upon 4 pi epsilon naught z d z alpha e square by r. This is daughter nucleus, that is Cm alpha e square by r. Okay. So which comes to this. VR comes to this. Now this alpha particle now at outer turning point VR2 equals to E alpha, which is 6.17 MeV. Okay, so say this is the outer turning point. So when we equalize this, we'll get the R. So that is 44.8 femtometer. So from here to here, this is 44.8. So what will be the range? So nuclear radius is 7.57. We calculate above. Outer turning point 44.8. So range is 44.8. So range is 37.37. So nearest. So answer is. So this is also a good question. Now we comes to our fourth question. So let's read it. According to the scattering experiment of electrons from various nuclei, the nuclear charge density rho CH as a function of radial distance r is approximated by relation. So basically it is asked what is the relation between the nuclear charge density as a function of radial distance. So how charge is distributed inside the atom. Okay. So this is famous Fermi Wood section distribution. So we know that. So this is the graph. So you can see that this blue line. So basically, almost most of the charge is accumulated here. Charge density is then it decays at the boundary level. So most of the charge is concentrated before the boundary. So this is the and this is the famous relation you have to learn. Rho naught 1 plus exponential r minus r. Okay, so option 1.